To save a little time in class answering questions about where equations are coming from, I'm going to show you how to derive the second order integrated rate law from a regular rate law in this video. Our regular second order rate law is going to look something like rate equals K and then some kind of concentration. We can use an arbitrary letter A squared. We can write a rate in the differentiated rate form with the dA over dt equals K A squared. Now we just got to separate our variables so that we can make things make a little bit more sense. So I'm going to move my dt over to the right and then divide over my a squared. That'll end up looking like k dt on the right and 1 over a squared times dA. Almost forgot, going to move over my negative sign to the right side so it'll make my equations look pretty later. Now I'm almost ready to integrate. Unfortunately for me, I don't like looking at my math in fraction form when I'm doing integrals unless it's 1 over x. 1 over x squared is a little bit weird for me. So I'm going to change this guy to a more convenient form really quickly. And now this matches what I see in my mind as a regular integral rule. Now we're ready to integrate between time equals 0 and time equals t, and from our initial concentration to our final concentration. And just as a little side note, I did have to look up my integrals because it's been a while, and the integral of any kind of x variable to an n with regards to x is going to be 1 over n plus 1 x to the n plus 1. And now I'm ready to set up my integral. We'll integrate the a side first, going from the initial concentration to the concentration at time t of the a to the negative 2 dA equal to our integration between time 0 and time t of the k dt, keeping that negative sign in front of my integral for convenience. We will follow our integration rules and write the answer to the integral up at the top on the right, doing our 1 over negative 1 times a to the negative 1 between the initial concentration and the final, or rather the concentration at time t, equal to a negative kt between time t and time 0. Now I'll put in my variables and simplify that 1 over negative 1. That's just silly. Here I'm going to try and keep track of both of my negatives by not distributing in my head. It's always pretty wise to keep track of your negatives that way. And in this part, I know that when I put 0 into this equation, it's going to equal 0, but I like to write it anyway just to keep track of what's happening with my math. So this whole second part of the equation, that'll be 0. Now we'll simplify to make it a little bit easier to see. We'll have the negative 1 over a at time t plus 1 over a initially equals the negative kt. Now the last part of this is just to simplify our equation so that it looks like the linear version of the equation that we see in textbooks. So what I'm going to do is I'm going to subtract over my initial concentration and then we'll end up with our equation having every single thing in the equation be negative, which is a little silly, but we'll fix it momentarily. And what we're going to do is we're just going to divide the entire equation by -1, which eliminates all of these negative pieces. So that is our integrated second order equation. And just like our last video, I want to stop and show you guys really quickly what that would look like graphed. It should look like a line, as long as what you're graphing is 1 over the concentration, with the x variable being time, of course.